back, everybody. I ended last time with a proof that the square root of 2 is irrational. As I mentioned last time, the reason that this was a big deal was because the Greeks did not have the same. They didn't have the same algebraic tools that we have now. So now we have something that we take for granted, which is the real number system. Constructing the reals from scratch is something you might not have ever thought about. But this was something that, to put it on solid logical footing, actually took a lot of work. And you take for granted that multiplying square root of 2 by 3, right, where 3 could be the length of a segment, and that square root could be the length of an arc of a circle or something. You take for granted that you are able to do that in the realm of algebra, completely untethered to geometry, right? And the Greeks didn't have that luxury, so this caused an issue. So let's see here. Question about the homework for number 2 of the 5,000. Oh yeah, I saw your email right before class, Ben. So you don't have to write it in cuneiform. So you can write it using the numerals that you're fond of. You don't have to use cuneiform. I don't even know what it exactly would look like in cuneiform. I would have to look at like the Plimpton tablet to see some of those things written down like that. Any tips for number 4? So the tip I will give you from number so hint for number 4 from the homework. You can turn this into a quadratic, okay? It can be turned into a single quadratic equation in a single variable. Now, the reason I put quadratic in quotes here is that one of the strengths of algebra, really, and thinking about equations more generally, is if I ask you what is a quadratic equation, right, the thing that you might write out would look like this, and that's certainly true. Okay. But what about something like this? What about would you call that a quadratic equation? You might look at it and say, that's not a quadratic. But if I define u to be square root of x, right, then what does this become? Well, then u squared is x, and so rewriting this, I get a times u squared, so I have ax here, so since u squared is x, this is a u squared plus bu plus c is equal to 0, which is a quadratic in u, right? Similarly, right, if I have ax to the 6th plus bx cubed plus c is equal to 0, this is also a quadratic, since I can say let u be defined to be x cubed, then u squared is x to the 6th, and this equation becomes au squared plus bu plus c equals 0 again. Now you might say, wait, how does this help me? Well, once you have a quadratic equation, you have the quadratic formula, right, which was known to the Babylonians. So you have the quadratic formula. Okay, so once you have the quadratic formula, then what do? Well, you apply the quadratic formula to find solutions for u. you're tossing out negative solutions because negative numbers weren't a thing that were noticed by these scribes, so these were tossed aside. You toss aside the negatives in this case, and then you'd say, oh wait, but I wasn't actually asked to solve this equation, I was asked to solve this one. So I found the equation solved for u, but then u is this, and I can then further solve in terms of x by using this this fact that I've done this change of variables. Okay. So you can turn that system into a quadratic. Now, the actual numbers, the other hint / advice I'll give you, I think I included this on the homework, or maybe I didn't. But the other advice is there are big numbers showing up, right, in the homework. So early on, I would rewrite those, right? So instead of having, what is it? I think it's a number like 3.2 million, right? So instead of having something like that floating around in your calculations, just rename that C, right? And the other one's 1200. So instead of having 1200 floating around, rename that something, right? Rename that whatever, alpha, right? Whatever you want to call it. Just name these symbols that are easier to deal with algebraically than writing, these numbers over and over and over again. Okay. So this is, trick to save your sanity so that you don't have to write these things over and over and over again. Okay, so let me know how that goes. Like I said, if you need more time on it, it's not a big deal. You don't have to worry about getting it in strictly with that deadline. So if you have more questions about it on Friday, you can let me know, and we'll discuss it. If there's too much issue with it, maybe I'll do part of it or some of it in lecture. So anyway. So we take for granted the real number system, which allows us to multiply. We got no problem multiplying 3 times square root of 2. That's not an issue. We can do that. Absolutely no problem. We can take an angle measurement and multiply it by a number. We can take fractions, right? So 1/2 times, square root of 5 over 2. It's absolutely not a problem for us. But the issue for the Greeks is that they didn't have an algebraic way of dealing with expressions like this because all of the expressions involved were coming from geometry. And so all of these things were geometric quantities, and so it didn't really, even multiplication of these things didn't necessarily make sense. So to give you an idea of what I'm talking about here. So the Greeks knew the following. So Greeks knew... this isn't an exhaustive list of all the algebraic identities they knew, but this is just some to give you an idea. So let's say the distributive property, right? So A times B plus C is equal to AB plus AC. They knew that. They knew how to square a binomial thing. So A plus B squared is A squared plus 2AB plus B squared. Okay. Now, how did they understand these quantities? But they understood these geometrically. Okay, so both of these facts were interpreted by the Greeks to be coming directly from geometry. Okay, so how is that? Well, here's an example. Let me focus. So this top diagram shows the distributive law. How does it show the distributive law? Okay, well, my first here. So the first line I have here, A times B plus C, that's the area of this large rectangle. What's on the right, AB plus AC, are two smaller subrectangles. So going back, A times B plus C is the area of this entire rectangle. But notice that that area is exactly the same as the area of this smaller rectangle plus the area of this other smaller rectangle. But what are the areas of those rectangles? AB and AC, right? So AB and AC are those individual areas. And the area of the whole thing is A times B plus C. Okay, so the distributive law can be seen directly from this rectangle. In writing, this is directly from Euclid. Okay, so this is the second book of the Elements. So this is exactly how Euclid explained this diagram. If there are two straight lines, and one of them be cut into any number of segments whatever, the rectangle contained by the two straight lines is equal to the rectangles contained by the uncut straight line in each of the segments. So Euclid was saying that not only do you have the distributive law in this case, Euclid was actually describing a generalized distributive property that applied to any number of cuts, he said. So he was actually saying that if you have A times B plus C plus D plus E, then you get AB plus AC plus AD plus AE. That's what he was saying. So he was saying you could do this for any number of cuts there. An example of this second fact, A plus B squared computes the area of a square having side lengths A plus B. Okay. So here's my square having side lengths A plus B. Okay. So then A plus B squared is the area of this entire big square. A squared is the area of this subsquare. B squared is the area of this other subsquare. 2AB is the sum of the area of these two rectangles, the dimensions of which are, of course, A and B, A and B. So A times B, I add those together, that's 2AB. And so this expression, right, this identity is again in terms entirely of a geometric diagram. Okay. I'm going to read another passage from Euclid. So if a straight line be cut into equal and unequal segments, the rectangle contained by the unequal segments of the whole together with the square on the straight line between the points of section is equal to the square on the half. What was Euclid saying there? If you actually trace through what he's saying, it is the identity A plus B times A minus B is A squared minus B squared. The difference of squares formula is what I just recited. Okay. All right, so all of these things were understood geometrically, and that's why it was such a problem that these incommensurable lengths existed, because there was no way of algebraically understanding, okay, this is a real number, multiplication of real numbers, like I get it. There was none of that. Okay, and so it took, as we'll talk about later, a guy by the name of Eudoxus set forth what was called a theory of proportion that allowed the Greeks to be able to deal with these incommensurable lengths algebraically. Okay, which was actually a pretty big feat. It was something that was actually quite impressive and doesn't get enough attention, because the logical underpinnings of what was going on wasn't actually set out until the late 1800s, early 1900s. So this is a pretty big accomplishment to make it work. Of course, this was a flaw in the Greek methods. This inability to do certain things algebraically because of hamstringing themselves by insisting on using this theory of proportion or not being able to algebraically deal with these things otherwise. It was a flaw. It was something that definitely held them back. And so, of course, many people argue that this could have been offset by a better number system. Okay. So anyway, maybe I'll mention one more thing. So the Pythagoreans came up with a way to approximate square root of 2 arbitrarily closely by rational numbers. So, of course, the Pythagoreans were the ones to come up with, or to understand, that square root of 2 is not a rational number. It cannot be written as a ratio of two whole numbers. But they actually came up with a method of coming up with rational numbers that were closer and closer to square root of 2. This process would never, of course, yield a single pair of rational numbers, the ratio of which was the square root of 2, but it would get them arbitrarily close. So how did they do this? So we're going to use modern notation to express this rather than the way that the Greeks did it, but this is exactly what they did. So I'll ask the question, how? So here's an explanation of this method because I find it to be interesting. I won't go over, I won't work out too many examples here, but I just wanted to show you this method. So if x squared minus 2y squared is equal to either plus or minus 1, okay, where x and y are positive integers, okay, what does this mean? Then x squared is approximately equal to 2y squared, i.e. x over y is approximately equal to, well, if I divide x squared by y squared, x squared over y squared is approximately 2. So x over y is approximately equal to square root of 2. And so the Greeks associated integer solutions to this type of equation to approximations to square root of 2. Okay, so those of you interested in number theory or applications of number theory, this is a very, very early, I believe this is the first example. I could be wrong, but I believe this is the first example of specifically tying this sort of approximation to integer solutions to some equation like this. Okay, and so what can we do here? So that thing that I just moved the paper on, so the Greeks understood this difference of squares formula, and so what we can do is we could actually think of this left-hand side as being a square, a difference of squares. So it is x plus square root of 2 times y times x minus square root of 2 times y. Okay, and of course that is, well, let's go ahead and actually divide through. Let's divide through by y. I mean, we could say that this is, yeah, let's divide through by y actually, and so that we can write this as a difference of squares. So maybe I will, I'll go ahead and do my division by y here, so that this becomes x squared over y squared minus 2 is equal to plus or minus 1 over y squared. Right? So I took my equation here, I divided both sides by y squared. This is the equation I get. Now I treat this as a difference of squares. Treating this as a difference of squares, this is x over y minus square root of 2 times x over y plus square root of 2 is equal to, so if I square both sides, or if I write this as a difference of squares, this is going to be x squared over y squared minus 2, which of course from this formula is going to be plus minus 1 over y squared. Okay. So then I can divide both sides by x over y plus square root of 2. So x over y minus root 2 is then equal to plus or minus 1 over y squared times x over y plus square root of 2. Okay. Now, Square root of 2 we know is bigger than 1, and there's a number of ways you know that. You know that square root of 1 is 1. You know that square root of 4 is 2. This has to be between 1 and 2, so this is definitely bigger than 1. So x over y plus square root of 2 is bigger than 1. So since x over y plus root 2 is strictly bigger than 1, this absolute value, if I take the absolute value of x over y minus root 2, this must be strictly less than 1 over y squared. Okay. And that's because you're dividing here by a quantity that's strictly bigger than 1, right? So this has to be, if I take the absolute value, that eliminates plus minus here. So this has to be strictly less than 1 over y squared. Okay. So, what is this? This is an error estimation. Right? This is an error estimation. This says that x over y minus root 2, the distance between those, how close those are bounded above by 1 over y squared. What this error estimation says is that if y is big, this quantity, 1 over y squared, is small, and so that x over y that x over y and root 2 are close to one another. So what this says, this says if y is large, then x over y and root 2 are close to one another. And so if you can find integer solutions to this original equation where y is large, you have found a very good approximation for square root of 2. So I'm not going to write out exactly the process for doing this. I'm going to show you all how this was done. So the Pythagoreans also came up with a way for generating positive integers satisfying this equation. Okay, so they started by initializing a sub 1 to be 1, b sub 1 to be 1, and then they defined inductively the n plus first step is the nth a plus 2 times the nth b, and the n plus first b is the nth a plus the nth b. And so if you generate a table here and consider the ratio a sub n over b sub n, you start out with 1, 3/2, 7/5, 17/12, just by computing these. And as you will see, so it turns out that these, if you look at the algebra here, at the n plus first step, so this is using induction to show that that a sub n, b sub n sequence solve this equation. These provide integer solutions. And so if you just iterate this process, looking at these ratios, notice they're getting closer and closer to what you know square root of 2 to be, right? So you know square root of 2 is roughly 1.414 and so on. So this is 1, 3 over 2, 7/5, 17/12. If you check all these, you'll see you're getting closer and closer to the square root of 2 here. If you continue this process, you can get as close to square root of 2 as you want to get. Okay, so it's a pretty ingenious method that the Pythagoreans discovered for approximating, this number that vexed them so much. Okay, so actually in doing so, they managed to find all positive integer solutions to equations like this, which is something that I don't think they noticed. So this method was originally described by Proclus, commenting on a passage in the Republic. So method first described by Proclus, commenting on Plato's Republic. But it was known to the Pythagoreans. Okay. So I thought that was interesting. That was an interesting little side blurb. Okay. So now I'm going to do kind of a survey of the mathematical developments, or I'll mention some things related, primarily going to be focusing on the mathematical developments, but this is philosophical developments and specific contributions from Heraclitus to Democritus. So So you have heard these names before, both in this course and in general from outside. Heraclitus is sometimes known as the weeping philosopher. So Heraclitus of Ephesus. So this is modern day Western Turkey. So he lived roughly around 500 BC. There are many other names I want to mention here. So Parmenides, who was a contemporary. Parmenides of Elea, which is southern Italy. Elea is Velia, which is an ancient city in southern Italy. So this is roughly 480 BC is when Parmenides was active. Zeno of Elea, which you have probably heard of as well. This is roughly 460 BC. Empedocles. So Empedocles was active in Sicily. He's not usually called of Sicily, but I just wrote that they're active in Sicily about 440 BC. And Democritus of Abdera, which is in northern Greece. So this is about 420 BC. So this is a progression of philosophers. And in many cases, what we'll talk about mostly is not necessarily their mathematical contributions, but it's definitely things that led to, so Zeno specifically, led to nice philosophical considerations that influenced the philosophy of math. So I'm not going to be writing as much for this description just because it requires me to. I have to say a lot. Until I get to Zeno, I won't be writing that much. So Heraclitus is often called the weeping philosopher. I mentioned him before, because in the context of this idea that everything is constantly in flux, everything is ever changing. Aristotle mentioned that the Pythagoreans believed that there was like a list of objects and their opposites in the universe, and so the universe is kind of a collection of objects and anti-objects. So they had a list. The Pythagoreans had a list that was one, many, finite, infinite, male, female, etc. So the Pythagoreans tried to understand, in one of their attempts of the universe, or to understand the universe, tried to list out every possible thing and its opposite. Okay, and so Heraclitus, basically, all things are in flux. All things are a struggle between obstacles. So all things are obstacles, opposites. All things are in flux. All is struggle between opposites. And the thing that I mentioned before when I said all things are in flux, Heraclitus is the philosopher that's credited with saying that you can't step into the same river twice, right? The idea being that all the water that was in the river at that snapshot in time is now, if you step in river one day and then 10 days later you step in what you think is the same river, well, the water that you stepped in is clearly different water, right? Whatever water you stepped in 10 days previously has already flowed down the river, right? So it is not the same river, in that sense. And so that's what is meant by you can't step in the same river twice. And then philosophically, that was carried over to everything. Essentially, there was evidently change, meaning that all things are in flux. Even something you know, even something like a statue, right, that you might think of as stationary, it changes. It cracks eventually, right? So maybe day to day it's things you don't notice. It's subtle, but there's still change. So this was the Heraclitian point of view. So everything is in flux. He also believed that the fundamental substance was fire, and he believed that all matter could be transformed into fire, and vice versa, that fire could be transformed into matter. And the example he gave was just as goods could be exchanged for gold, and gold could be exchanged for goods. He believed that this you could do this with matter as well. So ironically, the most Heraclitus was kind of most influential on more modern philosophers from the 20th century on, or from the 19th century on, through Hegel. So Hegel was greatly influenced by many Greek philosophers, but specifically Heraclitus. So if you have discussed or read much philosophy with a Hegelian bent, then there's some Heraclitian ideas floating around there. Hegel taught that there's thesis and antithesis forever struggling to produce synthesis, and so this is very much a Heraclitian sort of idea here. So the other point of view of Heraclitus, which the textbook notes Heraclitus has not had much influence on logic, because all things are in flux. What this meant logically for the Heraclitian worldview is that A is not necessarily equal to A. Right? Which logically is pretty hard to deal with, right? This is kind of a crucial underpinning of logical systems. And so this throws a wrench in all of that and makes logical deduction basically impossible here. So there's been some talk that I'm a little less familiar with about trying to deal with Heraclitian ideas as far as logic goes. And the textbook actually mentions this too. This is the notion of building math out of adjoint functors, which is something I'm not going to talk about too much because it would take me way too long to go through all that background. So this was the Heraclitian point of view. The point of view of Parmenides was kind of diametrically opposed to Heraclitus, which is funny since Heraclitus, believed in struggle between opposites, and Parmenides was definitely had the opposite view. So Parmenides had the following view: basically, nothing changes. So nothing ever happens, right? So there is no flux. Nothing changes. Change is an illusion, right? So change is an illusion. Okay. So this is, imagine, right? The point of view of the goddess is what Parmenides referred to. If you're familiar with some of the arguments made against determinism, scientifically, right? There's Laplace's demon, which is, imagine, there is some entity that has a perfect perspective, right? Some external perspective. In the eyes of this entity, so Parmenides said goddess, the past and future are just there at the same time, right? So there's past, there's future, and it's all accessible, all there at the same time. So nothing is really changing. Change is an illusion. And so this is not that at odds with modern physical descriptions, depending on who you talk to. This idea of to an external observer, you're observing, like we experience the slices, but an external observer can see all the time slices simultaneously. There's nothing is really changing. It's like flipping through pages of a book. So on a particular page of the book, nothing is changing, right? The only change is happening is in the flipping. This is, and actually our textbook uses the example of Feynman diagrams to show how like this is actually very much in the spirit of kind of a modern physics discussion. So the most important thing to glean from this is that Zeno was a student, a student of Parmenides. And if you are familiar with what I'm about to say, then you already see where this is going, because this philosophy of nothing is changing, change is an illusion, very much underpins what Zeno is most famous for. So Zeno was a student of Parmenides that posed a few thought experiments known as Zeno's paradoxes. Okay. So Zeno is well known for Zeno's paradoxes. So Zeno claimed that these paradoxes showed that motion is impossible. Or rather, that what we see as motion is actually an illusion, right? Maybe motion is an illusion is a more apt description. Okay, so there's 4 forms these paradoxes took that are kind of the most famous framing of these, which are the following. So there's 4 of them. So I'll list the first one. So imagine that you have a point on a number line moving from 0 to 1. Okay, so my goal is to move from 0 to 1 to show that motion is in fact possible. Okay, but let's say that the way that this motion occurs is, I'm moving along, right? And then what happens is I'm at the halfway mark. So the way that my motion is going to happen is I'm going to be at the halfway mark. And then at some point I'm going to, of course, half my distance to half the remaining distance, right? So first I'm going to be at the halfway mark, which of course is 1/2. And then I'm going to cover a distance of half of that, which of course is 1/4 from that. So if this is a distance of 1/2, now I'm covering a distance of 1/4, right? And if I half my distance to this one again, right, then now I'm moving a distance of 1/8. And if I half my distance one more time, I'm moving a distance of 1/16. And so if I view myself starting at 0, and I prescribe this process, right? So I say, start at 0, half your distance to 1 every single step. Okay. Will you ever touch 1? Will you ever actually reach 1? Well, first of all, what is the distance? What's the total distance that I'm traveling? Right? Well, I travel 1/2, then I travel an additional 1/4, then I travel an additional 1/8, then I travel an additional 1/16, and so on, right? Okay, and after some finite number of steps, I've traveled some 1/2 to the n, right? Okay, but we know what this distance has to equal. This has to be 1. But we actually know how to sum this. So the sum of these terms, the reciprocals of powers of 2, the sum of these terms is something that I can compute. This is actually just 1 minus 1 over 2n, or 2 to the n, sorry. Okay. So how can I compute this? This is the same trick I used to rewrite the earlier sum that I did, the finite sum that I showed could be rewritten. It's the same kind of algebraic trick here. And so this is 1 minus 1 over 2 to the n. So note, right, there is no n for which 1 minus 1 over 2 to the n is equal to 1. Right? Well, that's just another way of saying that there's no number of steps here, right, that I could take that would make this quantity equal to 1. Right? But that's the distance I'm traveling. And in order to go from 0 to 1, I have to travel one distance, 1 unit in distance total. But I can never do that. So it doesn't matter if I do this 100 times, 1,000 times, 57 million times, I'm never going to travel 1 unit of distance. I'm always going to travel a little bit less than that. And so motion is impossible, right? I can't even travel a single unit, right? It's impossible to travel a single unit in this way. So what is it that's going wrong here? Why is it that this paradox is a paradox at all? So what is it that Zeno is not understanding here? So what? Well, it's not that Zeno isn't understanding something. It's more that Greeks did not have a way to deal with the type of quantity that's showing up here. Okay? I.e., how do I resolve this problem? Right? So what is the modern take on this? Well, it is true that there is no n for which 1 minus 1 over 2 to the n is equal to 1. That's true. Okay? So, unfortunately, right, like, it doesn't matter how many steps you take, any finite number of steps you take is still not going to be enough. That's true. But if you were to allow this process to continue indefinitely, okay, then you will reach this distance eventually. And the way that we understand this is we say that the limit as n goes to infinity of 1 minus 1 over 2 to the n is 1. And so yes, this quantity never reaches 1 in a finite number of steps, but at infinity it reaches 1. Now maybe you're not that convinced, right? Maybe you're not that convinced. You say, okay, I don't like where this is headed. Okay, what's going on here? The way to think about this is the way that limits are defined, and I'm not going to write down the epsilon delta definition of limits or anything like that. So I'm not going to write down anything like that. I'm not going to write down the actual definition of a limit. But intuitively, the idea behind a limit was that if you specify me some error window, right, some error tolerance, okay, then if I'm claiming that a sequence or a quantity has a limit that I'm claiming it does, that means that I can get as close as you want. So if you specify that I get within 1/100th of that, then I can show you exactly how to do that. I can show you exactly the n, right? Exactly how many steps need to occur before you're that close. And if you move the goalposts on me and you say, oh, well, I want it to be even closer. I want it to be within 1/millionth, right, of that number, of that quantity. Then I could give you a new n that would make that happen. Okay, so I would tell you a new number of steps that you would need to take in order to be that close. And so the idea is that no matter what error tolerance you give me, I can always do that or better. So if you can keep making it stricter and stricter and stricter, it doesn't matter how strict you make it, I can still get it even closer. And so mathematicians came up with the terminology of limits as a way to really formalize this idea that it's arbitrarily close, okay, so that it is indistinguishable at infinity to consider this quantity being equal to 1. That's the idea. Okay, so Greeks didn't have the notion of limits, so this was completely out of reach. And Greeks would never have a proper notion of limit. The proper notion of limit wasn't a thing until much, much later, right? Until you get to the 1600s, there wasn't a notion of really understanding how these things work. The only exception is Archimedes came very close, okay, and we'll discuss that at length. So that's the first of Zeno's paradoxes. The second of Zeno's paradox is Achilles and the tortoise. So what is the idea here? So the story is the following. Achilles and the tortoise are engaged in a race along a measured line. So Achilles starts at 0, but the tortoise is given a head start at 1 since Achilles runs twice as fast as the tortoise. Thus, when Achilles arrives at the point 1, the tortoise is at 1 plus 1/2, right? So we have, here's Achilles, right, at 0. Here's 1, and here's my tortoise. Okay. The idea is that by the time Achilles gets to 1, even though he moves twice as fast, right? So he's twice as fast. So he has moved length 1 in 1 instant of time, and the tortoise has moved here. So when Achilles gets here, the tortoise is here at 1 plus 1/2. Okay. When Achilles arrives at 1 plus 1/2, where's the tortoise? Well, the tortoise is here at 1 plus 1/2 plus 1/4, right? So you see the relationship between this paradox and the previous one, right? And so on. So this process continues. So in general, so when Achilles gets to the sum, so we know that we can write the sum as 2 minus 1 over 2 to the n minus 1, right? The tortoise is at 2 minus 1 over 2 to the n, right? So what does this seemingly imply, right? Achilles is always behind the tortoise at any step here, right? At any n step, Achilles is always behind the tortoise. So Achilles can never catch up. Is seemingly what's being implied here, right? So no matter how many steps occur in this race, right, in this process, Achilles is always going to be 1 step behind, right? How do I resolve this? Another way of formulating this in a modern sense would be as sequences, right? So if you think about these number of points as terms in a sequence, what this is saying is that the tortoise starts at the first term in the sequence, but Achilles starts at the 0th term. So Achilles starts at a sub 0, and the tortoise starts at a sub 1. And so if you have two sequences defined in that way, so they're both parts of the same sequence, they're subsequences, right? But one begins 1 step further, right? Well, what this means is that at any point in time, the tortoise is one step ahead of Achilles in terms of the sequence. Okay, and that can never be remedied. No matter how much time passes, the tortoise is always one step ahead. Okay, so what is the problem here? Again, the problem is with limits. Greeks didn't understand limits, so the resolution is that the limit as n goes to infinity of 2 minus 1 over 2 to the n minus 1 is equal to this limit as n goes to infinity of this quantity describing where the tortoise is. So these two quantities are actually the same, right? They're both equal to 2, right? Both these limits are equal to 2, but the point is that these limits are the same. And so again, for a finite n describing this process, it is true that Achilles is never going to catch the tortoise, okay, for finite n. But as you let n tend to infinity, and what that means is that as n gets larger and larger and larger, I can get arbitrarily close, right? I can always find some n that gets me to within a specified error window. Okay, and this is the notion of a limit, but this was something that wasn't in existence for another 2,000 years. Okay, so this was not something available to Zeno at the time. Okay. Now we have two more Zeno paradoxes to discuss, also showing that motion is impossible. But I think that they're actually, these are very important. These are very important things to understand because with relatively simple thought experiments, Zeno exposed some flaws in the way that arithmetic was being done. Right? This was something that you can't answer either of these paradoxes without the notion of limit. Okay, so these paradoxes are true paradoxes before you develop the notion of limit. Okay, so like I said, we have two more to discuss, and then I'll move on to mathematics in Athens, and on to Plato and Aristotle, and more familiar names, moving on quickly to Euclid. Okay. So, I think that's it for now. Like I said, if you have more questions about the homework, just let me know before class on Friday. And if you need more time, it's not a big deal. So, anyway, I will see you all on Friday, where, like I said, we will start with Athenian mathematicians.